All right. So now I'm going to jump into where I was last time. I had started to talk about intermolecular forces, and the one that I did talk about was something called an ion dipole force. And ion dipole forces only matter when you have an ionic compound that's dissolved in a polar solvent like water. Well, they won't dissolve in anything else, but anyway, so what we're dealing with in this unit is liquids and solids, pure liquids, pure solids, and we're not going to see any ion dipole forces until the next unit. But I do want to move on. I said there were 4 types of intermolecular forces. Intermolecular forces, which I've always referred to as IMFs. And I did one last time. That was the ion dipole. And this time I'm going to start with the dipole-dipole force. And this is, you know, the business of having these dipoles, and that there are forces that come about because a molecule has a dipole. That's why I spent all that time last week on how to figure out if there's a dipole in a molecule. So dipole-dipole forces are between 5 and 25 kilojoules per mole. If you remember, the ion dipole was more like 40 kilojoules per mole. So these are not quite as strong as those. These are attractive forces. Actually, these are all attractive forces that we're going to talk about, attract molecules to one another. But these are attractive forces that exist between polar molecules only, because you have to have a dipole to have a dipole-dipole force. So for example, if you had an HCl molecule, just a very simple case, chlorine has a electronegativity considerably greater than hydrogen. If you looked it up, you'd find that it was 0.5 or above. And so you would have a delta negative and a delta positive like this. You'd have a dipole going in this direction. Okay, so if you have another Cl molecule next to it, HCl next to it, I'll just draw it the opposite way, delta negative, delta plus. This arrow is going the other way, okay? And you could say that there are attractions represented by this dotted line. And these are dipole-dipole attractions, okay? I could also draw it another way. You could draw it HCl, HCl, and, you know, just putting in the delta charges. How do I know that one is delta plus and one is delta minus? What would I have to do to figure that out? Oh, what did this thing do to me? Well, I will not be able to get that other thing. Yeah, all right. Yeah, I can't find my, you know, sometimes OneNote does this to me and I can't find my files from last time, but oh well. Well, I was just going to say that what you can do to figure this out is you could look it up on the electronegativity chart, and you'd find that H is like 2.1 and Cl is like 3.0. So the difference in electronegativity you could look up. Chlorine's is bigger, which is why we say the arrow points toward the more negative atom. And then you could draw your attractive forces like either a dotted line like that or something like that. And this is representing the dipole-dipole force between the two molecules. So, I mean, these are very simple, the simplest molecules you can get are diatomics like this, 2 atoms. But how about a more complicated molecule? And certainly these forces exist in more complicated molecules. So here's one. This is one that's a very well-known molecule that if you ever get to take organic chemistry lab, you'll be using a lot of this. It's called acetone. And it's actually CH3, C double bond O, and then another CH3. There are many ways to write these. You could write it like that. You could write it like this. That's a shorthand. You'd have to know that this O is double bonded to the C if you saw it written like that. A lot of times it would be written like this. Putting the C here, H3C, because that's that C that's bonded to this next C. But I'm actually going to draw it even better than that. I'm going to draw it with the correct geometry, because I want you to think about, you know, these angles here. What are these angles? What is this angle? Is this angle 180 degrees? Okay, so the answers to those questions are, well, this is not 90 degrees. This is not 180, not 180. This is not 90. This is not 90. So just because it's drawn, you know, and it shows those angles does not mean those are the real angles. How do you figure out the right angles? You look at the number of electron groups on that atom. Okay, here you have 3. So that's going to be trigonal there. So acetone, I really could draw it like this to draw it the best. You know, you draw that angle as a true angle, and then you'd have these CH3 groups, which I'm still not really drawing correctly because this would be tetrahedral, right? And I'm not drawing the 3D there. Okay, but what I want to do is show you that this molecule has a dipole, because if you look up in the electronegativity chart, you will find that oxygen is more electronegative than carbon, considerably more, so that you actually have a delta negative and a delta positive on the acetone there. Okay. Now, what about this region of the molecule? So this is like the polar part of the molecule. But then you've got these non-polar parts of the molecule. And there are 2 of them, right? And the reason they're non-polar is because there is not enough of an electronegativity difference between carbon and hydrogen, or carbon and carbon. There's none between carbon and carbon to have any kind of a dipole. So, but you do have a dipole moment in this molecule. Yeah, because oxygen is 3.5, carbon is 2.5, so there's a difference of 1, which is certainly big enough. And carbon and hydrogen, we've done that already as a not big enough and a difference in electronegativity to be polar. So acetone is polar, and that means that 2 acetone molecules will attract each other by dipole-dipole forces. And I give you an illustration here that, oh, this is not my file. I wonder. All right, I gotta start this again. Oh, what the heck? It exchanged my folder, my file, with some other thing that is not. I just don't understand how this happened. Well, that's all right. I'll fix my notes up later once I figure this out. Well, I'll have to fill this in later when I go to post my notes, but this was the folder now. I have it. All right. So this might not look like what I just drew, but it actually is. So let me show you why. So here I have C double bond O. O is always red in these crazy space filling models.
You're not sharing your screen.
Okay. So there's a black carbon underneath here, and then there's so that's an acetone. This is the delta negative and the delta positive end. I can draw this in red so you know that that's actually the red atom there, red atom. And that if you draw another one next to it, so basically this is like the delta positive part of the molecule. This is the delta negative part, and they attract one another like that. So you can kind of draw it that way. Okay, and this would be the dipole-dipole force. Okay, so that's just, you know, it happens in more complicated molecules as well. Your dipole is going this way, and they are attracted to one another. All right, so that's dipole-dipole. So the next type of force is called dispersion forces. Well, the dispersion force. And this guy has many different names, okay? So you could take chemistry somewhere else, and the teacher might refer to it as London forces or van der Waals forces. Or even, and this is actually the most descriptive force, but it's the longest as well. How about this? Induced dipole, induced dipole forces. Okay, so that's a bit of a mouthful. All right, so but what these are is these forces exist between molecules that whether they're polar or not. So all molecules have dispersion forces. You can see why I picked dispersion. It's just the easiest thing to say. And a lot of books use dispersion. So I would say that these are relatively weak. But I would also say that they add up. Okay. So sometimes they're pretty important. They can be important. And we're going to see an example of that later. Maybe next class. I'm not sure what will fit in today. And what they're caused by, this is the interesting part, okay? They are caused by distortions in the electron clouds of atoms and molecules. I'm just going to say molecules because we're really dealing with mostly molecules. So how do I illustrate a thing like this? Okay, well, I'm going to start by showing you what it might look like in an atom. So if you have an atom, nice atoms are very symmetrical, right? You've got your nucleus here with a positive charge. And then, you know, electrons are more like waves in atoms. They're not really single electrons. So I like to draw it as kind of, you know, I'll put a little dot for electrons, but really I'm going to also take my pen and just like do this to show the electron cloud. And what I show you here is a rather symmetrical electron cloud where it kind of envelops, you know, around the nucleus, but it's very symmetrical. But what can happen is at one instant, just for an instant, you can have the electron cloud kind of flop over a little bit to one side, which is, you know, hard to illustrate in anything but an exaggerated way. So I'm going to just do it in the exaggerated way. So let's suppose that at one instant, your nucleus is still over here. But now you have these electrons and the electron cloud with it kind of flopped over to the right side. Now it's never going to flop this much. It's just going to flop a little bit. But what happens is because these are the electrons with the negative charges, right? That they're going to be on one side And so you will have a little dipole. This is a temporary dipole, otherwise known as an induced dipole. Right, it's a temporary dipole. So then what, and actually this can happen in molecules as well. All right, so if I draw a very simple, say I have, just like maybe ozone, O3 looks kind of like this. So you have a nice symmetrical electron cloud distribution. Okay, here's your electron cloud. It's nice and evenly distributed. But at one instant, if that changes, and you still have your 3 nuclei, but now the electron cloud is kind of pushed over to one side. Let's kind of draw it like that, all right? And so we have more electrons down here. More electron density. I think it's too close to the edge. More electron density here and less here. See? More electron density. So you get this temporary dipole. So this can happen whether it's in molecules or in atoms. It's happening all the time. And what happens is when you get that distortion and you get a temporary dipole, so a temporary dipole induces a dipole in the opposite direction in a neighboring molecule or atom. So it's like, just because one molecule has this temporary dipole, a molecule next to it will, if it has a temporary dipole, it becomes attracted, and that's a lower energy. So that happens. So you have one molecule like this to exaggerate the situation. Something like this. And it has a dipole in this direction because you have more negative here, more positive here where the nuclei are. And then you'll have an inducement of a dipole in the opposite direction with a delta negative here and delta positive here. So this is, like I said, an induced dipole interaction. This is an attraction. This is an attraction of the temporary dipoles. Now, since these dipoles are not permanent, right, because these molecules are not necessarily even polar, that this is going to be, attracting, and then the cloud will change and it won't attract anymore. So this type of intermolecular force comes and goes. It's not constant. All right. So we get this inducement of a temporary dipole in a neighboring molecule, and that is pointed the opposite way. And these temporary dipoles attract. But they are constantly being made and then being broken up. Broken up by motions, broken up just by the motion inside of whatever this is. So anyway, that's what a dispersion force is. And this is just a picture of it I found somewhere, just like what I just drew. So this is really repetitive. That's just repeating it. There is something new here, though. I want to say, well, what does this force depend on? Because we're going to need to know that if we're going to try to figure out, what type, how large dispersion forces are, say, in a particular molecule. So I want to point this out right here, that this force increases with the number of electrons in the molecule. That's very important, okay? And how do you figure out, if you look at a molecule, if it has more electrons or less than this molecule over here. And the way to do that is, the easy way to do it is to just look up or find out the molar masses. If you have a large molar mass, then you're going to have a lot of electrons, or a lot of protons too, because as the atomic number increases, generally the molar mass will increase as well. So molar mass is a good thing to look at to see how big the dispersion forces are going to be in that compound. And I want to also point out, which I've said before, well, I haven't said this before, but it is true. This type of force exists in nonpolar molecules. And it's the only type of intermolecular force that exists between nonpolar molecules. So I actually should say between nonpolar molecules to be right. Now, I said that the size of the electron cloud determines the magnitude, the strength. I hate when I do that. Of dispersion forces. But why? Why is it that the size of the electron cloud is so important? And the answer to that is, when you have these big electron clouds, usually that means that the electrons are not held as strongly by the nucleus. You have a large electron cloud, it's usually further away from the nucleus. Okay, so that's true. Larger electron clouds are generally further from nuclei and are held less strongly. Because one big thing that matters a lot in terms of how strongly held electrons are is how close they are to the nucleus. That Coulombic attraction, that's what it's called, between a negative and a positive charge, depends a lot on the distance between those charges. So if it's further, so that would mean that larger electron clouds, if they're held less strongly, they can more easily distort. Okay. And this ability, so this is actually a word given to the ability to distort the electron cloud of an atom or a molecule. And that ability is called polarizability. So it's the ability to become polarized, right? The ability to have its electrons move away from its nuclei, at least to some extent. So if I was talking about, if I was going to compare two diatomic molecules, say Cl2 and I2, okay? So which of these is more polarizable? And that would be the larger one, right? Because so iodine is further down on the periodic table. It's much larger. It can more easily distort its electron cloud, and it's more polarizable. It will have greater dispersion forces. Okay. All right, that's 3 out of 4. Okay, we've got the ion dipole, the dipole-dipole, the dispersion forces, and the fourth one, which is absolutely a terrible name, but it's a very important intermolecular force, and it's called hydrogen bonding. Put that in quotes. I put that in quotes because I've said many, many times that these are intermolecular forces, okay? These are forces between different molecules. So they really should not be called bonds. These are not covalent bonds. They're not ionic bonds. They're not covalent bonds. They're not bonds in the true sense of the word. So why is this called hydrogen bonding? Oh, I don't know. It's because some old guys in history decided to call it that and never thought about how teachers are going to teach chemistry students about this years from now. Anyway, so anyway, that's why. It's just tradition. So why this horrible name, tradition? Or just remember, please. These are not true bonds. They are intermolecular forces. Okay, so let me explain what it is, because now I've just talked about the name, I haven't said a thing about it, okay? Another word for this, it's actually a special case of a dipole-dipole force. In fact, sometimes we call it super dipole-dipole. Well, that's why it's been seeming so wide and big. It's okay. I'll just make it a little bigger. It's a special case of the dipole-dipole force. In fact, sometimes it's called super DD because it's stronger than a regular dipole-dipole force. And here it is, okay? This is what you have to have hydrogen bonding, okay? You have to have a hydrogen that's covalently bonded to either an O, an N, or an F, okay? So that's the first thing you have to have, the hydrogen covalently bonded to O, N, or F. And when a hydrogen is covalently bonded to one of these three, okay, these are the most electronegative elements in the periodic table. So that is going to mean that you have a considerable dipole, okay? So you have a delta negative here on whatever atom this is, and a delta plus over here. So you have a serious dipole here. Okay, so you have a strong dipole. Now, that's the first thing you have to have. The second thing you have to have is that there has to be an O, an N, or an F on a neighboring molecule. Okay? And then this could be bonded to anything. I'm just going to call it etc. Okay? The rest of the molecule. And so now you get this hydrogen bonding attraction between these two. Okay, so you draw a dotted line here. This represents what we call a hydrogen bond. Okay, and it is it is the strongest intermolecular force. Anyway, so the hydrogen that's covalently bonded to O, N, or F is attracted to an O, N, or F on a negative molecule, which of course is delta negative on that molecule, because whatever it's going to be attached to is also going to be less polar than it. So that is a situation that you have to have in order to have this super dipole or special dipole-dipole force. So, and these are stronger. These are similar in strength to ion dipole forces. These can be about 40 kilojoules per mole. Maybe not that high all the time, maybe 25 to 40. 40 would be the strongest type. So here's an example. The simplest example I could think of right now is if you have HF, hydrogen fluoride. Okay, this is the most electronegative element in the periodic table. It is quite delta negative. So you have this dipole here. And then if you have an HF nearby, so here you have F another H, okay? So here you have a hydrogen. It's covalently bonded to a fluorine that is attracted to a fluorine on a neighboring molecule. And so this is a, quote, hydrogen bond type of intermolecular force. Okay, does that make sense? Yeah, all right. Any questions so far about this? Actually, I would have a question if I was in the class. I would say, well, why? What is so special about that? So I'm going to answer that question, okay? So why is this attraction stronger than any old dipole, okay? Why is this such a big deal? And it has to do with the concentration of those delta charges, okay? So you basically have more concentrated delta charges. Okay, so what do I mean about that? Well, it has to do with the large electronegativity of fluorine, nitrogen, and oxygen. So F, N, and O are very electronegative atoms, but they are very small, right? They're on the first, well, hydrogen, helium, then you get lithium, beryllium, blah, 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 and you get some boron, carbon, nitrogen, oxygen, fluorine. So they're in the second period of the periodic table. And there's only 2 in the first period. So they're among the smallest atoms in the periodic table. So you've got this very electronegative atom that's very small. And so any delta negative charges, any extra electron density that's pulled over to these atoms is going to be pretty concentrated in a small volume, okay? So you get this concentration of these delta negative charges. And at the same time, obviously hydrogen is the smallest atom, and it carries delta positive charges, small positive charges, okay, but you know, that's the charges we're dealing with. And so this is more concentrated as well. Okay, and it's this concentration of the charge in smaller volumes that makes for truly the most important and the strongest intermolecular force, which we call, unfortunately, hydrogen bonding. Okay, so that's what it is. So I want to say that this is probably the most important thing I've said so far this semester, for sure. Hydrogen bonding is just like so important in biology and in life in general, really. It's chemistry as well. It's so important because it's everywhere. Okay, for example, if you have pure water, so you have all these molecules here, one here, then you might have another one here in the liquid pretty close together. You'll have another one here. Okay, and all of these have delta negative and delta positive, with the delta negative on the O and delta positive on the H. So you would have, there's a hydrogen bond. There's a hydrogen bond. You know, I could keep drawing more of these molecules, and there'll be more hydrogen bonds. There's absolutely a whole network of hydrogen bonds in pure water. Okay. All right, and I just really want to reiterate that the hydrogen bond is the intermolecular force between these molecules. It is not a covalent bond. So just to bring that point home even more, I'm going to show you an illustration. It's a picture of just sort of randomly placed molecules of water. So just to sort of show you, so this is a molecule of water here. And then there's another, they're all in different angles, so they look, a little different. Actually, I don't want to do that, because what I want to show you here is that this is this 0.96. So first of all, this unit that we're using here is the angstrom. 1 angstrom is 10 to the minus 10th meters. So it's pretty small, okay? So you can see that what this is showing in the picture is the size of a covalent bond. So the bond that's attaching this O to this H is 0.96 angstrom. So we're going to call that 1 angstrom. This is a covalent bond in H2O. Okay. This dotted line, this is a hydrogen bond. And let's use the one over here, because it actually has, it tells you what the length is. And you could see that this is about 2 angstrom. So it's basically twice as long, twice the distance. Okay, so it's not a real covalent bond. It's much further apart than a real covalent bond. Really double. And you could see here's another example of hydrogen bonding here. This one over here and over here, So all these covalent bonds are around 1 angstrom, but the hydrogen bonding between the two molecules occurs over twice the distance. So a covalent bond in water, if you think about how much energy to break it, because remember, it requires energy to break bonds. And I've given you that number. Does anybody remember that number? How much energy it would take to break a covalent bond, or a mole of covalent.
Avogadro's number?
Oh, no, that's a little too much. No, it's one of the numbers I gave in that envelope calculation. How much energy would it take to break up a mole of H2O molecules? A mole of OH bonds, I should say. There, somebody said it. Thanks, Chelsea. That's absolutely right. It takes 467 kilojoules per mole to break up the OH bonds in water. Okay. What would it take to break this hydrogen bond? That's also a number I've given you, but I'm going to tell you. It takes about 40 kilojoules per mole to break up hydrogen bonds, which, like I said, are not bonds. They're intermolecular forces. I will probably write that on most of your papers before the end of the semester, but anyway. So 40 kilojoules is a whole lot less energy needed to break up those intermolecular forces. So I would say that hydrogen bonding intermolecular forces are about 10 times weaker than OH bond strength. So 467 is more than 10 times 40, and that's why I say that. Okay, so hydrogen bonds, like I said, are they're strong for intermolecular forces, but they are nothing compared to, a real bond like an OH bond. Okay, so anybody have a question so far? Anybody? No? Kayla, you have a question? Okay. Well, maybe I'm going to go over some examples now. This is from an activity. Oh, I do want to say that this is at the beginning of the activities list. It's just this information. So it's telling you that this is chapter 10 in the OpenStax book. It tells you some things in that chapter that are not covered. Sometimes I supply additional information, as you probably already know. But anyway, we're not going to do every one of these activities in class. Some of them, if we don't do them in class and you're not assigned to do them, you should do them at home. Make sure you know how to do them. But I usually at least mention them if I don't assign them. So anyway, here is activity 1. Okay. In a pure sample of each of these molecules, so in other words, it's only one type of molecule that's present. That's what I mean by a pure sample. It means you have only HBr or you have only CF4. Okay. In a pure sample of each, decide what kinds of intermolecular forces there will be. Okay. And then in order to figure that out, you have to figure out first if the molecule has a dipole or not. Okay, so if we look at this first one, we have HBr. And what do you have to do to figure out if there's a dipole? And this is why I wanted to look up my handy electronegativity chart here, which I have. So you can see that if you have HBr, Br is 2.8, H is 2.1. Make a copy of this chart for yourself so you can have it by your side, because it's very useful when we do these type of things. Okay, so, oops. So hydrogen, 2.1, bromine, 2.8. The difference is 0.8. That's greater than or equal to 0.5. So it has a dipole. Yes. Does it have a dipole force? Yes. Anything that has a dipole has a dipole force. Does it have dispersion forces? What do you think? I'm waiting. Oh, somebody said no, but that was wrong. So it must be yes. Okay, the reason that's wrong is because every single molecule can have dispersion forces. Whether it has a dipole or not, it could still have those temporary dipoles and induced dipoles. So does it have dispersion? Yes. Okay, and in fact, I could fill in yes for every one of these molecules. Can it be involved in hydrogen bonding? Can you have hydrogen bonding between two neighboring HBr molecules? And what's the answer to that question? No. Somebody said no. I'm going to believe the person who said no, because the answer is no. Because what do you need to have for hydrogen bonding? You need to have the hydrogen be covalently bonded to an O, N, or F. There isn't even an O, N, or F in this molecule. So that first criterion knocks it out. No. Okay, so let's move on to the next one. So what do you have to say about this one? Is there a dipole in CF4? Is the CF bond polar? What's the answer to that question? Yes, that's right, Erica, that's right. It's CF is polar, but we have 4 equivalent dipoles here. We have one this way, one pointing sort of towards us, one going back. And what happens when you have 4 equivalent dipoles in a tetrahedron? They cancel out. Absolutely, they cancel out. So the dipoles cancel. And it's quite a dipole, right? Because this is 4.0 and this is 2.5. It's a big dipole, but they cancel. So there is no net dipole. Net means just the sum. It cancels out. So the answer is no. So is there a dipole-dipole force? No, because there's no dipole. Is there dispersion forces? Yeah, I should get a chorus of yeses. And I think I am. I'm just like not keeping up with the chats very well. Okay, good. So can there be hydrogen bonding? Can there be hydrogen bonding between CF4 molecules? I'm getting no's. I like the no's. The answer is no. Why? Why can't? Well, first of all, there's no H, right? You have to have an H that's covalently bonded to an O, N, or F. So you got the F, but you don't have the H, so no. All right, what about this one? CH2F2. So let's think about it. Does this have a dipole? So we know that there's a dipole here and a dipole here because it's the same CF as we had before. You know, fluorine is 4.0, carbon is 2.5. Take the difference. It's definitely polar bonds between C and F. Okay. But yes, I'm getting a lot of yeses. Yes, there is a dipole because there aren't dipoles from C to H that would cancel those. So you have two, they're not pointing 90 degrees, they're pointing that tetrahedral angle 109.5 degrees apart from each other. But there's basically a net dipole looking something like this. It's going to be kind of like in between them. I was trying for a different color, but that didn't seem to work. Where's the other color? So there is a net dipole here. Okay. Is there a dipole-dipole force? If you have a dipole, you have a dipole-dipole force. Are there dispersion forces? I see somebody's nodding their head. Yes. You always have dispersion forces. Okay. And what about hydrogen bonding? So this is to think about, right? So what do you need for hydrogen bonding? You need an H covalently bonded to O, N, or F. I see no's. I see lots of no's. The answer is no. Okay, why not? I mean, let me draw a picture here. Here's one molecule. Whoa, I think I got too many. Okay, and let's say I have another one next to it. Why can't I get hydrogen bonding between these two? What do you mean not direct?
Is it because the H's are connected with the C, the carbon, and so because of that, it can't be?
H is bonded to carbon, not O, N, or F. And an H that's bonded to carbon is not even polar. It doesn't have a delta positive charge because the CH bond is considered nonpolar. So the H is not delta positive here. Okay, and even if it had a little, it may have a slight delta positive, but it has to be bonded to O, N, or F, so that has a really serious delta positive charge. So this is the reason. So there is no hydrogen bonding there. Okay. What about this molecule? This is one of the ones we talked about last week. Remember, you have this lone pair sticking up here. So N and H, the NH bond, N, electronegativity, let's take a little, look it up. Nitrogen, 3.0. Hydrogen is 2.1. So delta En is 0.9. That is definitely polar. Okay, so we have 3 dipoles, 1, 2, and 3. Okay, and they're all pointing in sort of their left-right might cancel. They do cancel. The left-right does cancel, but they're all pointing up. There is a net dipole that points up, at least if the nitrogen is on top. If we turned it upside down, it would be pointing down. Okay. So is there a dipole? Yes, there is a net dipole. They don't cancel. Does everyone understand why they don't cancel? Or have a question? Is there a dipole-dipole force? If there's a dipole, there's a dipole-dipole force. So yes. What about dispersion forces? I mean, this is almost a trick question at this point because the answer is yes to all of them. All atoms and molecules have dispersion forces. And here's the next question is there hydrogen bonding? Is there hydrogen bonding? So let's take a look. I'm not going to draw the 3D version. I'm just going to draw it like this. So we have here a hydrogen that is covalently bonded to a nitrogen. And this hydrogen could come in contact with a nitrogen on a neighboring molecule. I'm going to draw it like this. Okay, so here is a nitrogen on a neighboring molecule. And there is an attraction that is called a hydrogen bond or hydrogen bonding. Okay, so yes, there is hydrogen bonding in ammonia. That's ammonia. Does that make sense? Okay, so definitely NH3 has hydrogen bonding. What about pH3? I don't know, does anybody have an electronegativity chart handy for them to look it up in? You have to first figure out if there's a dipole. And the electronegativity of phosphorus, we know what it is for H, because it's 2.1, we've used that. What is it for P? Oh, 2.1, yes. So guess what? They are the same. So the difference in electronegativity is 0. Okay, so there is no dipole in pH3. So there is no dipole-dipole force. Yes, there are dispersion forces. And no, there would not be hydrogen bonding. It isn't even an O, N, or F. We'd have no polarity in this molecule at all. Okay, good. All right, let's see. What about H2CO? I'm going to think about it for a minute. I'm going to show you the electronegativity chart so you'll have that. And in fact, I'll even draw the molecule here. And I've drawn this molecule. You might see this molecule written like this. You know, there's all kinds of shorthands. And if you see the molecule drawn like this, you have to say to yourself, that's not really drawn right. That's not the right angle. It's still it's a structural formula, but this is one that shows the proper geometry. Well, either way, you'd still have a dipole, but I just wanted to say that because you will see it like that. So does this molecule have a dipole? Well, first, let me ask, what is the difference in the electronegativity between carbon and oxygen? One. Yes, it's 1.0. Exactly. So that means that that bond is polar. And then remember, you have to ask yourself, is it going to cancel? Well, there's absolutely nothing to cancel it with. Okay. You have a delta negative, a delta positive, and these are non-polar. So nothing is there to cancel it. Actually, I should be writing this in the other one, so it's in the notes. Oh, well, sorry. So we have dipole. So we have dipole-dipole forces. Of course, we have dispersion forces always. What about hydrogen bonding? Why is it 1.0? DeLon, did you look at the electronegativity chart? Hold on. Carbon is 2.5, oxygen is 3.5. Yeah, so delta En is 1.0. Does that take care of your question? Okay. All right. Well, there is no N, O, N, or F in this molecule, so there would be no hydrogen bonding. Oh, what am I saying? There is an O. Yeah. So why is this answer no? Let's think about this. Why can't I have this going on? Why not? It's not bonded to O. H is not bonded to O. That's exactly right. H is not covalently bonded to O. In fact, H is bonded to carbon, but the CH bond is considered nonpolar. So the H isn't delta positive at all. Right, she's right. Somebody, Sarah said they aren't linked. Yeah, the O and the H are not linked. When you see an O that's linked to an H, any molecule that has that will have at least some hydrogen bonding between molecules, but not in this case. There is no hydrogen bonding. The O is not linked to the H. That's correct. Okay. Oops, what happened? Okay. All right, now propane. Now, I just want to point out about propane here, again, that this is one of these ways of drawing these molecules, but we know better. We know that this is not a straight line. We know that we have tetrahedral angles here. And so these are not 90 degrees. It doesn't really affect anything in this problem because we don't have any polarity, right? There's really no polarity. What do I mean by that? No polarity. There is no bond that has an electronegativity difference 0.5 or greater. No bonds have delta En of 0.5 or greater. Okay. So there is no dipole, there is no dipole-dipole force, and there is no hydrogen bonding. But yes, always there is dispersion forces. we would say there is no permanent dipole, not no permanent charge. That's how kind of how we would say it, just FYI. Okay, and now we have very interesting molecule, propylene glycol, which is used in auto antifreeze and stuff like that. And what I did was I drew it in the kind of like showing you what the geometry is. But there's an interesting little tidbit I can tell you. If you think that this molecule always looks like this, you would be wrong. When you take organic chemistry, you will learn that all of these single bonds have what we call free rotation. That all of these bonds can literally rotate, so that this OH might swing over to this side and not be there. You know, it's rotating. So when I draw this, what I'm sort of doing is drawing an instantaneous picture. I just want you to know that. But when you look at propylene glycol here, you see that you have oxygen and hydrogen. You know that that's got a dipole, right? And you know the same thing between carbon and oxygen. So you have basically a net dipole here that looks like this. And similarly over here, and the other OH, COH, you have a dipole pointing this way and a dipole pointing that way. So you have kind of a net dipole that looks like that. And really, the only question you have to answer to figure out, is there a dipole, is, well, we already figured out that there are dipoles, but do they cancel? That's the important question. And unless they are pointed opposite of each other, right, in equal and opposite directions, or like I said, the 4 bonds of a tetrahedron, or 3 bonds in a trigonal structure, you know, and none of this is like that. You know, we have these 2 net dipoles, these big blobs here, big arrows I'm drawing, and they don't cancel. You could see that they don't cancel. They're not pointing in equal and opposite directions. So the answer is no. There is no, they don't cancel. So yes, there is a dipole. And the next question is there a dipole-dipole force? Yes. There are always dispersion forces. Now, what about hydrogen bonding? What do I put here? And I know the diagram is kind of a mess because it's big giant arrows, which I'm going to get rid of now. I'm just going to put them back as small. This is the net. Here's the net. Somebody said yes, and the answer is yes. So I'm going to try to draw it for you because it said here on the bottom. Oh yeah. If any of these compounds can form hydrogen bonds, draw 2 and show dotted lines representing those hydrogen bonds. So I'm going to actually draw it the easy way, right? Remember I said that, you know, when we draw these molecules as flat, it doesn't mean they're flat, but it's just easier for me to draw it like that. So I'm going to draw it like that. Okay, so what we have in this molecule is that on an end carbon and the middle carbon, there's an OH. So I'm going to do that, but I'm going to draw it in a flipped way. I'm going to put my carbons here. And here is my OH, and here is my O. Come on, erase you. What the heck are you doing? And so here I have delta positive, delta negative, delta negative, delta positive. So this is a hydrogen bond. And very specifically, it's from an oxygen. Well, you have a hydrogen that's covalently bonded to an oxygen that is attracted to an oxygen on a neighboring molecule. So you have hydrogen bonds, and there's many different ways you could draw them. I mean, depends on how you orient the molecules. Yeah, But anyway, that's one of them. Does that make sense? I hope so. All right. So why is the name hydrogen bonding so terrible? Can you explain that? Think about that. So terrible because it's implying by the term bonding that it's a bond, but it's an intermolecular force. Okay, so it's not a bond. All right. Wow. Okay. So I wanted to show you some hydrogen bonding in biology. So I have this illustration. And maybe you recognize this, right? These are the base pairs in deoxyribonucleic acid, DNA. And here's, adenine and thymine will pair together. So will cytosine and guanine. And these dotted red lines here, so this is like the et cetera of the DNA, right? There's more stuff here, but I don't want to bother focusing on that. I want to focus on what keeps that helical structure together and what it actually is. And you can see where it is, this is what I'm talking about. This is what's holding that double helix together, are many, many hydrogen bonds. So between adenine and thymine, there are 2 hydrogen bonds. Here is a hydrogen that is covalently bonded to a nitrogen that is attracted to an O on a neighboring molecule. This is a hydrogen bond, okay? Again, here we have hydrogen that is covalently bonded to a nitrogen that is attracted to an N on another molecule. And there are 2 between A and T. Between G and C, between guanine and cytosine, again, we have hydrogen that's covalently bonded to a nitrogen that's attracted to an O on another molecule by a hydrogen bond. I could go through these. Now, this is actually not the same slide as the one I put in the packet. This is the one I put in the packet. Well, I looked at this one today and I was like, well, that's not right. Because notice between adenine and thymine, this shows 3 hydrogen bonds. And this shows, and I remember that it's not 3 for both, it's 3 for one and 2 for the other. So what's wrong with this picture? This is not quite right. I've been using this slide a couple of years and I never realized it before today. They played us like a fiddle, exactly. Yeah, right. This hydrogen here, it's not bonded to an O, N, or F. So you take these things off the web and you think, oh, this is going to be right. It looks great, beautiful picture. And this is actually like an incorrect. This is not a hydrogen bond. And that's because this is not an O, N, or F. I thought that was pretty funny because it caught me for years, or a couple of years anyway. Anyway, so now you know to look more critically at things sometimes. Anyway, all right. So I want to tell you, I wanted to talk about protein folding a little bit, but I really don't have time to do this. So I made a little video. I actually made it last semester and I watched it this morning. It's about 10 minutes. And it talks about the role of hydrogen bonding in protein folding. I don't know if you know this, but proteins are generally folded in a certain way And this is showing kind of a cartoonish structure of that, showing the alpha helices, and these are beta sheets here. So I think you should, watch this video, and it tells you some sort of stuff that's very closely related to what we've been doing today. So you should watch that. There's actually 3 videos. So the first one is on protein folding. The second one, I think the second one is on intermolecular forces. No, actually the second one is called, I don't know which is which, but surface tension and viscosity. And then there's one called intermolecular forces and structure. That's what it's called. No, it's called liquid properties and structure. So this one, the protein folding one, you could watch right now and understand it. These two, I think after today, you probably would be able to understand them. And you're responsible for this material. I don't think we're not even really covering surface tension and viscosity during lecture. So you should definitely watch that, or you won't know what those properties are. And liquid properties and structure kind of puts it all together, which supplements what I do in class about that. I do put it together in class, but this shows you tables and compares numbers. And I think it's a very pretty good video. So, well, I don't know. I mean, my job, it's a pretty good topic and summarizes it pretty well, I think. So these are all the links are on Blackboard under Unit 2, solids and liquids. You'll see them there. Anyway, so you should definitely watch those. So what I'm going to talk about next, I've talked a bit about liquid water, right? I've said that liquid water, so in liquid water, there's lots of hydrogen bonding between water molecules. Okay, and we know that these are relatively strong intermolecular forces. So if you have a glass of water, so here's your liquid water here, okay, and here and so what you have, and I've said this before because we definitely needed to know this to solve some gases problems, that above the water, above the liquid, I should say, are gaseous water molecules. So you've got some, in there, okay? So you always have gas above a liquid, okay? And why is that? So why are there always gaseous molecules above any liquid, really? So what's the answer to that question? Why is that always the case? Anyway, so I'll tell you, okay, because you always are going to have some molecules that can overcome the attractions with their neighboring molecules and sort of break away. And like I said last time, I think I used the term escape to the gas phase, okay? Because always some molecules, I could say there will always be some molecules in the liquid, well, with enough energy to overcome attractions to their neighbors and break away to the gas phase. And you know, actually, that I've actually showed you the chart of the vapor pressure of water at different temperatures. So you know that this happens more and more as the temperature goes up. Okay. And that actually kind of answers the question of where does the energy come from, right, to do this? And the energy comes from the kinetic energy, the motion energy, which we know increases as the temperature goes up. Okay, so the energy to do this, so the energy to break away is supplied by kinetic energy you know, they're moving around, they have the energy to sort of break away, okay? The motion, kinetic of liquid molecules. And as temperature goes up, of course, there's more of that kinetic energy. Because as you know, temperature is a measure of the kinetic energy of particles, and that's true for the liquid as well as for the gas. So what happens if you take, and if you, oh, I'm not up to this yet, hold on a minute. If you leave a glass of water in the open, you know, you just leave it at home, okay, or wherever, and you come back, I don't know, 2 days later, it's empty, right? Okay, and the reason why is because the water has evaporated. So what happens is you have these gas molecules here above the liquid, and then later you have nothing. Did you see that? What happened? What did this thing just do? Oh, God, just threw away like a page of notes. What happened? Well, I'm going to have to work on these notes before I post them. Oh, well, anyway. Okay, so
I
later,
Control Z.
What? I did Control Z like 5 times. Didn't do any good.
That's
Thanks for the suggestion. Oh yeah, acetone. Yeah, acetone will vaporize very quickly. But anyway, it evaporates. But the question is, what happens? Wait a minute, hold on a minute. Yeah, so if you leave it there, what happens is that you know, so why does this happen? Let me just get this down a little bit. And, you know, that's clearly because there's nothing holding this gas in. The gas molecules diffuses away. And so when this diffuses away, you get more molecules going to the gas phase. Okay, and eventually you have nothing in the flask or the glass. So let's contrast that with the situation I'm going to show you here. And in this situation, I have a cover, I have a cap on these three. Okay, so now we cover the water flask. Okay. And so now we are able to establish an equilibrium. And this is what happens. And this happens basically instantaneously. Water molecules, some of them can break in the gas phase and form gas. But then when gas molecules start to build up here, so in this first picture, we basically have liquid evaporates. When you build up some gaseous water molecules here, we get some of the H2O gas condenses. They come together, they get a bigger droplet, they fall in. And eventually what happens is you have an equilibrium where you actually have equal rates of evaporation and condensing. And at that point, which happens very, very fast, at that point, there is a certain vapor pressure. I'm just going to write pH2O. Sometimes I call it P-vape, vapor pressure of water. In this case, water. Or you could say partial pressure of water, because it's the same thing above the liquid. And that's the thing that if you increase the temperature, you're going to end up with more vapor. Okay, you're going to favor the vaporization for a while until you establish a new equilibrium. And that's because at a higher temperature, you have more molecules that can break away into the gas phase. Okay, so now with the closed flask, at a higher temperature, more H2O will vaporize. And you'll have a greater pH2O or P-vape at the higher temperature. Okay, so I'm actually going to give you a little chart here of temperature in degrees C and the vapor pressure of water in torr, which is the same as millimeters of mercury. And you know, I've given you this chart. You have this big chart that I gave you, but I didn't go up to such a high temperature as I'm going to do now. So I'm just going to give you 4 values so you could see how this changes. At 20 degrees C, this number is 17.5. You know, atmospheric pressure is 760 millimeters. This is not very big compared to that. At 40 degrees C, this goes up to 55.1 torr. At 80 degrees, 320. This goes up rapidly with temperature. You're supplying more energy. You're giving more of those water molecules the energy to get into the gas phase. At 100 degrees C, this is 760. Do you know, what do you, look at this. This is a special number here because this, this pressure, this is actually 1 atmosphere. So at 100 degrees C, the vapor pressure of water equals 1 atmosphere, which is atmospheric pressure, which is that pressure outside. And in fact, that is the definition of the boiling point. So the boiling point of a liquid is the temperature at which the vapor pressure above that liquid equals atmospheric pressure. So this is the temperature when the vapor pressure above a liquid, Okay, nice. Okay. Great. Yes, we are in right in the middle of a definition, you know, it's not right. Oh, brother. Another problem. I hate Zoom. I may have to leave the meeting and come back. What time is it anyway? Oh, I know why. Okay. This might take a minute. So let me just finish that. Hold on. Okay, I got it now. Share screen. Not yet. Okay. The boiling point of the liquid, again, is the temperature when the vapor pressure above the liquid equals atmospheric pressure. And, you know, at sea level, like here in Rhode Island, this is 1 atmosphere, or 760 torr. That's what it is here in Rhode Island. So if you were on a mountain where the pressure was less, water could boil faster. That's true. I'm going to talk about that. But because, and what she means by that is, of course, if you live in Denver, which I actually used to live in Colorado, and I came across this firsthand, and you got to watch out when you're cooking because the pressure, all right, so at a higher altitude, so where I lived was about a mile high, okay, so the atmospheric pressure was lower, right? Thin air, so to speak. Okay, so that means that water would achieve the needed vapor pressure, which was lower, it would be at a lower temperature. Okay, so water would boil at a lower temperature at high altitude. And so what happens is that the water is boiling at a lower temperature. So if you're making rice, it's actually cooking at a lower temperature. So you actually have to cook it longer. And what ends up happening is you end up boiling off more water. So you have to add more water and cook it longer. It's just a different, you know, you have to adjust the cooking. One time I made a whole bunch of wontons and I brought them up to somebody's house in the country. It was like, I don't know, like at 8,000 or 9,000 feet. And they kind of almost fell apart before the pork inside cooked, because it was, you know, pretty stupid to do that. But, you know, live and learn. Anyway, we ate them and they were fine because we had gone hiking that day. But other than that, but anyway, I just want to get started showing you these curves. I just have a little time. So I'm going to talk about boiling point, but for now, I'm going to just talk about, well, that's one of the things you can get off of these curves. But what these are graphs of vapor pressure. That's what's on the y-axis, P vape, okay, versus temperature in degrees C. And the first thing that you notice here, I hope, well, first thing I want you to notice is that all of these curves are going up, every one of them. As temperature goes up, these curves go up. for all three of the liquids in this chart. And the liquids are ether, ethyl alcohol. It says it, but it's not that bright. And H2O, water. And actually down here we have ethylene glycol, but it's going up also, but it's a much higher boiling liquid. It's sort of out of the picture. So all of these curves, every one of them goes, the P vape goes up as the temperature goes up. And that's because as the temperature goes up, your molecules have more energy to break away from intermolecular forces. So as the temperature goes up, molecules have more energy in the form of kinetic energy to break away from each other. In the liquid. So you're breaking intermolecular forces and get into gas phase. So that's definitely common between all these things, okay? But what's not common about these three liquids is that these three curves are in completely different places on the graph, you know? They're shifted. One is to the very far right of the other, and another one is even further right. And so let's look at the differences now, okay? So we can see that they're all going up, but okay, what's different about these curves? So if we go to the next graph, it talks about that. So what the next graph does is it takes a look at what is happening. So this focuses on 30 degrees. So one temperature. So here's 30 degrees over here, this line. Okay. So you could see that at 30 degrees, that's what I'm talking about here. At 30 degrees C for water, water has a vapor pressure of about 30, I'm going to call it torr for millimeters of mercury. Okay, sees water down here. Here's water's curve. And this is about 30, okay, and it's at 30 degrees C. Ethyl alcohol, the vapor pressure is about 80 torr at 30 degrees C. But ether, which is this curve here, ether, the vapor pressure, look at this, is over 600 torr at 30 degrees C. Okay. So why is that? Why do we have these differences? So we have different liquid properties, different ability to get into the gas phase, which is going to result in different boiling points as well, which I'm going to go over. And yet, you know, what is it about these three molecules? And so I would like to talk about the structures of them because it's intimately related to this property. And here I'm going to, so this, if you look in a lot of books, you'd see diethyl ether. Diethyl ether is this compound over here. Okay, but I just want to point out that, well, maybe I need to ask you guys, what is this angle here? Is this really 180 degrees? So let me ask you first, what's missing in this picture? This picture doesn't include the lone pairs. Don't forget, if you see an oxygen with two bonds, you have to ask yourself, where are the rest of those electrons? So notice I put in the two missing lone pairs here. In fact, I'm going to write them in red so that you know that they're written in by me. Okay. So what is the electron geometry at this oxygen? Is it linear? Is it trigonal? Is it tetrahedral? What is it? How many groups of electrons on that central atom? Come on, count them. 1, 2, 3, 4, right? So what if there's 4 groups of electrons? What does that make this geometry here at that oxygen? Come on, folks, you can do this. Tetrahedral. Oh, 3 people told me. All right, good. So that means that this picture is not quite really right, right? You've got the lone pairs like that, and you have C, and of course, then you have, you know, this is not 90 degrees either, these angles, but I don't care, because all I care about is the fact that now I know I have a dipole here and a dipole here, and those dipoles do not cancel. Which is why I brought this whole thing up, right? Because if you look at this molecule here, the way it's drawn, you think the dipoles cancel, but they do not cancel because the angles are not, that angle is not 180 degrees there. It's not linear. So you have to be very aware of what the actual, you know, structure is. So we have a dipole there, but we don't have any ability to form hydrogen bonds. Let me give you the structure. Here's water. We know the structure of water. This is the diethyl ether. These are all hydrogens here, by the way. And then we have ethyl alcohol. And by that, I do want to point out that on another slide coming up, you know, on these slides, I have these structures printed and I have explanation. So if you miss something, you can look at that later. But ethyl alcohol is like this. Well, I drew it kind of weird, but that's okay. So that's water, ethyl alcohol, and diethyl ether. Okay. And water had the lowest vapor pressure at 30 degrees. Diethyl ether had the highest P-vape at 30 degrees, and this was the middle. So I drew it in order of increasing vapor pressure here. So now the thing is that you should be able to explain based on their structures and what intermolecular forces they have, why ether has the greater has the greatest vapor pressure and water has the lowest. Okay, so what it means, okay, is first of all, let's talk about the type of intermolecular forces that are in here. So water can form hydrogen bonds. Well, ethyl ether, ethanol has an OH, so it can form hydrogen bonds between its molecules. Is there hydrogen bonding here? No, no hydrogen bonding, because the H is not bonded to an O, N, or F. So we already did that exercise, right? So if we look at this further, you could see that if you have a sample of water molecules, there are a lot of chances of hydrogen bonds forming. Every atom of a water molecule is capable of forming hydrogen bonds, right? Every atom. Can form hydrogen bonds to other molecules. In ethanol, you only have 2, we call them sites, for hydrogen bonding on a molecule. right? You only have an O and an H. These H's cannot be involved in hydrogen bonding because they're not bonded to O, N, or F. And here I said we have no nitrogen bonds. We have dipole-dipole though, but that's weaker than hydrogen bonds. And we also have dispersion. We also have dispersion here and dispersion here. Okay. So basically, water has the greatest intermolecular forces. It has the most possibilities of forming hydrogen bonds, which are the strongest intermolecular forces. It has the most possibilities of forming hydrogen bonds. And hydrogen bonds are the strongest intermolecular force. Ether, no possibility of hydrogen bonding. So and despite the fact that it has the greater molar mass and greater dispersion forces, you can see from its high vapor pressure that those molecules aren't having any trouble getting into the gas phase. So no possibility of hydrogen bonding and only dispersion forces, which really can't compete with hydrogen bonds. So ether gets into the vapor the easiest, the more easily. This water having more possibility of hydrogen bonds, strongest intermolecular forces, not many molecules, not as many anyway, can get into the vapor phase. Not enough energy to overcome these hydrogen bonds. And of course, ethanol would be in the middle, okay? It can form some hydrogen bonds, but not as many as water. So it's in the middle. Okay. All right. So I guess I have to end. I hope you had as much fun as I did, and I'll see you next time. Try to look at some of the videos. See you tomorrow in lab, if I have you in lab. Yeah. Have a good day.
All right. Have a good one. Bye.
You too. Bye.
Thank you.
For me, that went by very fast. I don't know about for you.
We absorbed a lot today. Thank you.
Bye. Does anybody have a question? Crystal, Madison, Erica? If not, I'll end the meeting.